Differential and integral calculus are used extensively in physical chemistry. In this module, we will review the essential relations of differential calculus that are crucial to the understanding of thermodynamic equations. Many quantities that we will encounter in physical chemistry are functions of several variables. For instance, consider a quantity f whose value depends on three variables x, y, and z. This relationship is represented in equation 1 as f equals another f, the second f being a function of arguments x, y, and z. Given the multivariable nature of the function f, we must modify the rules of differential calculus to take these variables into account. We introduce the concept of partial derivatives. When computing a partial derivative, we differentiate with respect to only one variable, while mathematically treating all other variables as constants. For example, equation 2 presents the mathematical notation for the partial derivative of f with respect to x obtained while y and z are held constant. This symbol, which originated as a stylized cursive small Latin d, is the sign of the partial derivatives. As with derivatives of functions with a single argument, the function being differentiated is written in the numerator, and the variable with respect to which the function is differentiated is in the denominator of a fraction. Variables held constant during the differentiation appears as the subscript of the differential fraction. It's worth noting that other mathematical notations exist. Similar to the partial derivative of f with respect to x obtained while holding y and z constant, we can also compute the partial derivative of f with respect to y obtained while holding x and z constant, and the partial derivative of f with respect to z obtained while holding x and y constant. An important property of multivariable functions concerns their second-order mixed partial derivatives. Here, second order signifies that we perform partial differentiation of the original function twice. Mixed indicates that we differentiate with respect to two different variables. The mathematical notation for the second-order mixed partial variable of f is the following: twice partial derivative of f in the numerator with respect to y and to x in the denominator. This is a concise representation implying that initially we determine the partial derivative of f with respect to x, and subsequently we compute the partial derivative of what we had obtained in the first step with respect to y. It's worth noting that derivatives are added from the left, making the order of differentiation potentially counterintuitive. Now we can present an important property of second-order mixed partial derivatives, their symmetry. Specifically, the order in which we perform partial differentiation is interchangeable. It means that if, rather than initially differentiating with respect to x and then to y, we first differentiate with respect to y and then to x, we obtain the same outcomes. This property is known as Schwarz theorem, Clairaut's theorem, or Young's theorem. Mathematically, for equation 5 to hold true, all second-order partial derivatives of the function f must exist and be continuous in the vicinity of the point where we compute the partial derivatives. We will continue discussing the mathematical properties of quantities that depend on several variables. Besides partial derivatives that describe the change of a quantity due to the change of one variable only, we often need to consider the change produced by changes in multiple variables simultaneously. This change can be expressed using the concept of a total differential. The total differential of a multivariable function f, denoted as df, represent its infinitesimal change due to infinitesimal changes in all its variables. If we continue with our example of the function f that depends on x, y, and z, we can express its total differential df mathematically. It is the sum of its partial derivatives with respect to each variable, each multiplied by the infinitesimal change in that respective variable. Thus, as depicted by equation 6, the total change in f is a combination of the changes due to each of its variables. Let's look at the following illustration. You are on a hill and have determined your altitude above sea level. How much will the altitude, denoted as z, change if you move a small distance east, denoted by x, and north, denoted by y? The change in z as you move east is the slope of the hill in that direction, the partial derivative of z with respect to x at constant y, multiplied by the distance dx that you move. A similar expression can be written for the change in altitude as you move north. Therefore, the total change in altitude is the sum of these two changes. Mathematically, the combined change of the height z, its total differential dz, is equal to partial derivative of z with respect to x multiplied by dx plus the partial derivative of z with respect to y multiplied by dy. An important property of the total differential concerns its integration. We refer now to the integration of a total differential, which is an infinitesimal change of a certain function of multiple variables, from point 1 to point 2 along a specific path in a multidimensional space. The specific path from point 1 to point 2 is significant here because, unlike in one-dimensional integration, there is an infinite number of possible ways from point 1 to point 2 in a multidimensional space. By performing the integration, we accumulate all infinitesimal changes of a function f that were encountered along this path into a single finite sum, which is an integral. So, it turns out that when we integrate the total differential from point 1 to point 2 in a multidimensional space, the result is actually path independent. The value of the integral remains the same, regardless of the chosen path. More specifically, for any path between 2 points, the result of the integral equates to the function's value at the end point minus its value at the starting point. The finite difference, or a change of the value of f when transitioning from one point to another, is often denoted by the capital Greek letter delta. Furthermore, from equation 7, it's evident that the integral of a total differential over any closed path, where the start and end points are the same, is always zero. Mathematically, this property is represented in equation 8. In fact, the properties of the total differential expressed in equation 7 and 8 are equivalent. In the previous slide, we had demonstrated that a multidimensional integral of a total differential derived from a multivariable function depends only on the starting and end point of the integration path and not on the specific path. We can pose a question: can this relationship also be applied in reverse? Let's take a differential form of two variables dq as an example. dq is equal to a times dx plus b times dy. Here, a and b are functions that describe how infinitesimal changes in independent variables, x and y, result in an infinitesimal change we call a differential form. Suppose we have discovered that the integral of dq is consistently path independent. Does that signify that dq is a total differential? The answer is yes. In this scenario, dq is a total differential, also known as an exact differential. Moreover, once we have confirmed that a given differential form is a total differential, we can always identify a multivariable function q, termed in this context a potential function, whose partial derivatives yield the initial total differential dq. Returning to the initial expression for the differential form dq, given as equation 9, what further insights can we derive if we are certain that dq is a total differential? According to the definition of a total differential, a and b are merely partial derivatives of the potential function q with respect to x and y. Moreover, a and b are not arbitrary functions. There exists a specific relation between them. Namely, the partial derivative of a with respect to y must be equal to the partial derivative of b with respect to x. This relation arises from the symmetry of the second-order mixed partial derivatives, and both expressions are equivalent to the second derivative of q with respect to x and y. Now let's look at a general differential form in a multidimensional space. It is given by this equation. dq is equal to the sum of infinitesimal changes in all independent variable xi, each multiplied by a certain coefficient di. Every di is in turn a function of all independent variables. If we are talking specifically about total or exact differentials, the following properties are equivalent and allow us to determine if a differential form is a total differential. There exists a potential function q whose derivatives produce the differential form dq. The integral of dq is path independent. Partial derivatives of coefficients di in the differential form are consistent with the symmetry of second-order mixed partial derivatives. That means that for any pair of independent variable xi and xj, the partial derivative of di with respect to xj and the partial derivative of dj with respect to xi must produce the same result, which is in fact equal to the second-order mixed partial derivative of the potential function q. If a differential form exhibits any of those three properties, it is a total differential, and it exhibits all of these properties. In the opposite case, if a differential form fails to exhibit even a single property of the total differential, then it does not exhibit any of those properties and is thus not a total differential. Such differential forms are named inexact differentials. Both total or exact and inexact differentials are mathematical constructions that are widely used in thermodynamics to formulate its principles and to derive certain natural laws from these principles.